All right, welcome. In this video, we're going to be talking about how to analyze functions with technology. And me personally, I'm going to be using a TI-84 for this video. But all of these things are things we could do on Desmos or with a different type of calculator or, other forms of technology. Okay, but the reason I'm using the TI-84 is that that's what we have on my campus. That's what most of my students have, and that's one of the approved calculators for the AP Pre-Cal exam. You're not going to be able to use Desmos on that. You're also not going to be able to use Desmos or your phone or anything on the quiz in my class, so that's why I'm going to just model the use of the TI-84. All right, here's a little list, as you see on screen, of skills that we need to have after today with the calculator. We need to be able to solve an equation. We need to be able to compute average rate of change. We need to be able to graph a function, find zeros and intersections, and find locations of relative maxima and relative minima. So let's get to it. Let's do all those things. All right. First, we want to solve an equation. So we want to find the values of x that make this equation true. And what we're going to do is we're going to solve by graphing. Okay, I recognize that there is an equation solver in the TI-84, but I'm not that good with it. I'm not nearly as good with it or as fast with it as I am just graphing these things. So let's pull out the calculator. Right. If I'm trying to solve this equation, one thing I could do is I could graph y equals natural log x on one curve and y equals 1 over x as another curve and see where they run into each other. And I think that's what I'm going to do. Okay, there's the graph of y equals natural log x. Maybe you remember that from Algebra 2. Maybe you don't. That'd be all right too. We'll study that function in its own right later. Okay, we're going to come over here and we're looking for the x value of their intersection because that would tell me where, what x gave me the same y's for these two y's. All right, so I'm going to calculate, and that's right here. That's really where all the good stuff is on this calculator. So we want to see where these two graphs intersect. So we're going to choose option 5. And the first curve is blue. I don't know, I was graphing on TI-83 in class, and I needed to scroll to the right to make sure I was actually on the blue curve before it would let me select that one. Second curve is going to be the red curve. As for a guess, and that's going to be more relevant where there's more than one intersection, which we'll see on the homework, but not right now, but you can scroll over and, get right there. All right, now it says, all right, I found it for you. X equals 1.763 and y equals 0.567. And the 0.567 is not without meaning, but the solution to this equation, that's the x value. So that's going to be x equals 1.763. Now, I don't think I mentioned it on the previous page, but in AP Precalculus, just like in AP Calculus, we're always going to round to 3 decimal places. Okay, and this one was one where, rounding and just cutting off after 3 was the same thing, but you actually have the option, you can do either one, nobody's going to be upset. All right, so that's going to be how we solve an equation, or one way we can solve an equation, by graphing and finding the intersection. Okay, that 0.567, that's what we would get if we took 1 over 1.763, whatever, or also if we took the natural log of that number, we would get 0.5671433, either way. That's why that's the solution to the equation. All right. On the other hand, here we've got x to the 5 minus 4x to the 2 equals 2. And we could do the exact same thing. We could graph y1 equals x to the 5 minus 4x to the 2 and y2 equals 2. But there's, I think, a faster way. What we could do is we could set this equation equal to 0. We could have done this with the other one as well. It just wouldn't have been as obvious. We can set it equal to 0, throw all of this into y1, and see where it has an x-intercept. All right, so we're going to throw that into y1, graph the thing, hope it shows up on the window we're looking at. There it is, okay. It did hit 0 there, so we can figure out where this equals 0 by calculating a 0. That's option 2. It asks for a left bound and a right bound. So it's like, hey, give me a window to look in. And you could just, scroll around and click if you wanted, but I like to think about the two numbers it's between. It's between x equals 1 and x equals 2. And if it's close to 1, then I could just go with a slightly wider interval. Okay, giving it a guess, I don't think we really need to. There's only 1 0 in there. Yeah, 1.676. Oops. X equals 1.676. Always 3 decimals. All right, that's solving an equation. Let's move on to computing an average rate of change. So we might want to find the average rate of change of the given function on the given interval. And so I'm going to start with f of x, and then I will just show the result for g of t real quick, let you try it on your own, because I think this is something you'll be able to execute, without too much difficulty. So what we're going to do, we're going to bring back the calculator, and I'm going to just clear the RAM. You probably don't need to do that. I'm going to type in, now I've got the ability to call on a fraction bar with F1, and I really recommend that if you've got that ability. So fraction bar 4.7 divided by x to the power of 3. Okay. And now we've got it typed in there just right. Now we don't even need a graph for this. What we're going to do is we're going to actually have the calculator compute what we need it to. So if I want the average rate of change of f on the interval 1 to 3, that's going to be f of 3 minus f of 1 divided by 3 minus 1. And the calculator is smart enough, it can do this. Okay, so what we're going to do is we're going to, let's zoom in on that a little bit, say, all right, well, I'm going to need a fraction bar. That's the best way to do this. And then we're going to just have it evaluate f of 3 and f of 1. Well, we plugged f of x into y1. So we're going to call on y1, and we can get that out of the F4 menu. If you're working with a TI-83, you're going to get it out of the variables menu, and I will show you how to do that the second time I call for it when I get, f of 1. Okay, so the F4 menu is right here. See, look, it's a bunch of y's. So I'm going to choose y1 of, and the calculator is smart. It knows what you mean when you do this. Like, it knows you mean plug in x equals 3 and report the result. Minus, but if you don't have the F4 menu, you can still do this. You probably won't have a fraction bar either, but just be judicious with your parentheses and you'll be all right. Variables, y variables, we're in function mode right now. That's the old place where you used to have to go to access these things. So y1 of 1 divided by 3 minus 1. And if you're like really confident, you're like, I know what 3 minus 1 is, you could just type in 2 and that would be just fine. All right, and so this is one where we can round or we can truncate. Okay, if we round, we see negative 2.2629. That would be like negative 2.263. But if you just wanted to read off the first 3 decimals you saw, that would be completely fine too, and you could say that was negative 2.262. All right, now you try it on your own. Okay, compute the average rate of change of this function on the given interval and make sure you round to 3 decimals and hopefully get the same answer as me. You're going to want to do this with the video paused though, because I'm going to be bringing in the answers here in just a few seconds. So you can just go ahead and pause now. All right, there you have it. So I got 0.998 or 0.997, but I got that by plugging into y1 and then going out to the main menu and computing an average rate of change right there, and getting 0.9977. So we can either round or we can truncate, so give us one of those 2 answers. All right, next we're going to look at graphing a function and finding zeros and intersections. So the object was launched upwards from a height of 8 meters with an initial velocity of 12 meters per second. The height of the ball at time t is modeled by h of t equals negative 4.9 t squared plus 12t plus 8, where h is measured in meters and t is measured in seconds. All right, it wants us to sketch the graph of h versus t on the time interval where t is greater than or equal to 0, clearly from it only showing us the first quadrant. And we're not going to be interested in negative heights because I guess there's ground there and the object would just hit the ground and then the model would stop working if h went negative. All right, so I'm going to need the calculator. We're going to just plug into y1 and we're going to use x for t, and we'll just know that when we get results back, if they're results that say x, they're t values, and if they're results that are y's, then they'll be h values, right? So we're going to sketch the graph of h versus t. I'm going to change the window to be, I don't know, input 0 to input 10, because we don't need negative time here. And I think that should be enough, but okay, a lot of it is off the screen. So it went to a height that I could not see, so I need to change the window a little bit. Also, it hit the ground at what looks like t equals 3, so I don't need a whole lot after that. So I'm going to change the window a little bit. I'm going to change the input values, the t values, from 0 to 4. And then I'll change the output values from negative 10 to 10 to more like negative 1 to 20. I don't know how high it went, but I bet 20 should be good. And that should be a much better graph for us. And that actually kind of looks like what I could sketch in over here. All right, so it started off at what I bet is 8. It went up and then down. And that's a perfectly fine sketch. You don't have to be any fancier than that. So I'll label that. Okay, that's the sketch. Well, graph of h versus t. I could definitely label the axes if I wanted. Might be nice. Okay, and if it asks when the object hit the ground, it wants to know when is h equals 0. So when did this 0 happen? And it looks like t equals 3, but just because it looks like t equals 3 doesn't mean we're going to be able to just write down t equals 3. Okay, first of all, we need to be showing the setup that leads to our computations. Okay, if we're going to solve an equation, we need to write down what equation we're trying to solve. We're trying to figure out when is h of t equal to 0. And yes, I know we could use a quadratic formula on this, but we've got a calculator, so we might as well use that to our advantage. So we're going to calculate a 0. Okay, so that's finding zeros. Okay, we're going to calculate 0. And just like before, when I feel like oh yeah, when we did find a 0 when we were solving an equation. Just like before, okay, it looks like it's going to happen between, well, it looks like it's right at 3. So I'm going to say between 2 and 4. And then I get t equals 2.994. Okay, that's not the same as 3. Right? If we saw 2.9999998 or something, that might mean 3. There might be round off in the calculator or something. You can even see right here, it's having a hard time with the concept of 0. It thinks it's 1 times 10 to the negative 12, which would be 0 point, I think, 11 zeros and then a 1. That means 0. But getting used to that just comes with time. And then how long did it take for the object to fall from a height of 5 meters to a height of 1 meter? All right, so what we're going to need to do is we're going to need to find when does h of t equal 5, and when does h of t equal 1. Okay, so what we're going to do is we're going to graph 5, graph 1, and look for the intersections. And so y equaling 5 and y equaling 1. All right, so we go in, graph, there's an intersection, there's an intersection. We'll be able to find the difference in those t values and get ourselves an answer. All right, so we're going to calculate an intersection like we did earlier. First time I'm going to want blue against red. Okay, there's only one intersection, so I don't really need an accurate guess. That's going to be 2.678. But I want just to make sure that when I subtract, there's not anything in that fourth decimal that's causing, rounding or truncating or whatever to cause me to be slightly wrong in that last decimal. I'm going to hold on to that value. And what's nice is that the calculator, when it just did that intersection, it stored that x and y coordinate into the letters x and y. So I'm just going to hit x and press enter, and then see that's that 2.678 number, except it's got all the decimals right there, and it's going to remember that when I go back to the graph. Now, I'll need to find that second intersection, so I'm going to calculate an intersection, but this time it's between blue and black. So I'll press, first curve is blue, y1, but the second curve does not want to be y2, it wants to be y3. So I go down here and I select down and go to the black curve, that's y3 equals 1, select that one, that's my second curve. Guess, again, there's only one intersection, so it doesn't really matter, and that's going to be t equals 2.9356. Then if I quit out and I press X and press enter again, it's got the new number, 2.9356. So what I'm going to do is I'm going to take this number and I'm going to subtract that other number to get the difference in the two t values. Oh no. Okay, I forgot to put in the minus. Okay, I'm going to save me a little time. Okay, subtract these numbers and now I've got myself a suitable answer. Okay, so if I call this T1 and T2, the difference would be T2 minus T1, and I just use the calculator to compute that. That would be 0.258 or 0.257. All right. Now, actually storing those and computing those with the difference, it might not have changed my last decimal in this one, but there will be scenarios later in the course, I think, where we have to hold on to a value, use it later, and run it through a function, and that's where we're going to want to be storing values. So I just want to kind of point that out to you right now so that that's not something unfamiliar later on. Okay, now we need to find some extrema as well. So when did the object reach its maximum height? Okay, when, that's asking for a t value. So what I want is saying, okay, I want to find the coordinates of the maximum, and really I want the t coordinate of the maximum. So I go back to the graph. I see it's happening right about here. Okay, but I'm not going to use trace. That's not very accurate. I'm going to use calculate. Okay, calculate a maximum. Left bound, well, I know zero's to the left of it. A right bound, I'm pretty certain that 2 is to the right of the maximum, so I'm going to use that. Okay, 1 was a little bit close. I'm pretty sure 1 is to the left of it, but just to be safe, let's just say 0 to 2. And then the maximum's happening at x equals 1.224 and y equals 15.346939. All right, so the maximum height, that's going to be an h value, and catch that that was happening. All right, so when is going to be the input, the t value, that's x equals 1.224. So t equals 1.224. And the maximum height was, y, the h coordinate. H equals 15.347. Or 15.346. Now, I know I mentioned this verbally earlier, but I didn't actually show you. I don't know why we would need to do this at this point, but if you did need that number, you could just type in y, and it would give you that 15.346938878 number. Okay, and I think that's enough info on that. All right, find the average rate of change in the height of the ball from the time it is at its maximum height, which we just found to be 1.224, but I think is actually also stored in here. Yeah, there we go. Okay, minus, and then the time it hits the ground, we already found that one as well. That was the 2.994 number. Okay, now, do I have that one? 2.994. No, I did not. Okay. But what I could do is I'm going to go over here and I'm going to calculate the 0 one more time on blue. And well, that's to the left of it. 4 is to the right of it, I guess. Okay, there we go. Okay, and I'm going to go over here and I'm going to grab this number. Oh, whoops. I was clicking on the wrong button. Oh, no, now I've got a fraction bar. That's not what I need. All right, let's do that. Yeah, that'll be better. Okay, now what I'm going to do is I'm going to store that number using stow into A, because that was kind of my beginning point. Okay, and then the time it reached the maximum, that was that 1.224 number. I'm going to store that one into B. And this is probably a little more fancy than we need to be, but I just want to show you these calculator tricks right now, since we're talking about calculator today. All right, so we press it, store right there above on, and then press enter. It's like, okay, now when you say A, I know you mean 2.994243542, all the decimals. So when I compute the average rate of change, I'm going to do f of B minus f of A over B minus A. Okay, and if I call this, well, I guess I'm going to call this T3 and T4. All right, I want y, or h of T4 minus h of T3 divided by T4 minus T3. Okay, well, I've stored T3 into A and T4 into B, so I'm going to just call for y1. Oh, no. Okay, I'm in here trying to call for y1 of B minus y1 of A divided by B, oh no, B minus A. It's a little frustrating having to click through all these things on the calculator. It's surprising how much faster it is with a handheld model. And then I get negative 8.672. Negative 8.672, or 671 if you like. All right, and so the average rate of change in the height of the ball, that would be negative, right? it's going down, the height is decreasing, so we would expect to see a negative average rate of change. Right, here's a question that's got a bunch of different parts, all going off of the same function, kind of taking the meaning out of it, just like here's f of x. Let's answer some questions. So we've got it typed into y1. We're going to zoom to the standard window, so that's zoom at 6, at least at first, until we know what we're looking at. All right, it's thinking, it's graphing. Okay, there we go, and nice. Okay, we can see almost all of the action, maybe all of the action here on screen. I'm a little worried about this. I feel like I can see the minimum, but I'm not certain, so I'm going to actually just let the y minimum go down to like, I don't know, negative 12. I don't need a whole lot more. I just want to be certain. All right, and so find the absolute minimum value of f. Okay, we haven't really talked much about absolute extrema, nor will we, I don't think. But an absolute extremum is like the most minimum value of x. See how this, minimum value of f, pardon me. See how here we have a local minimum here and another local minimum here. But this second local minimum is pretty clearly down lower. So this is the absolute minimum. So what we're going to do is we're just going to find the, okay, if it's a minimum value of f, it's going to be an output value, a y coordinate. We're going to calculate a minimum between x equals 2, 3, 4, and 6, right? So x equals 4 is going to be my left bound, x equals 6 is going to be my right bound, to give it a guess, and there I'll have it. Okay, so I was being a little paranoid and I did not need to extend the window. The minimum value of f is f of 5.281 is equal to negative 9.915. Okay, where the actual value of f is this number right here. Okay. Now we're going to find the average rate of change of f on the interval 1 to 1.5. Well, okay, we're going to write down the formula because we're always going to show the setup for our computations. Except for like the maxima, we can't really do that because the setup for those computations is calculus. F of 1.5 minus f of 1 divided by 1.5 minus 1. Okay, but I think you can try this on your own. Okay, so compute this with video pause. I'm going to bring it in 2 or 3 seconds. All right, there you go. I brought in a fraction bar, asked it to compute the average rate of change, got negative 24.375. Hopefully you're getting good at that. All right, find the values of x that make f of x less than 0. So we're going to go back to the graph and we're going to look at it. All right, less than 0. Okay, this looks like a bounce here at x equals 1. Okay, less than 0 is happening between these two x values, which looked like 4 and 6, and I actually saw when I was doing the minimum that those were zeros, but I don't know if you noticed that when I was typing in the numbers. Okay, so it's going to be on this interval, but I need to just verify and calculate the zeros. So looks like I've got a 0 at 4. I'm going to look between 3 and 5. Okay, yes, sure enough, that was 4. And then the other one, I'm going to calculate a 0. It looks like it's at 6, so I'm going to look from 5 to 7. And it was at x equals 6. Y was negative 3 times 10 to the negative 11, which means 0. And so that's going to be between x equals 4 and x equals 6. There's no real setup to show here because that was the setup that gave me the inequality to solve. All right, find the intervals on which f is increasing. Right, well, f is going to be increasing between this minimum and that maximum because it's going uphill, and then after that minimum. And I have already computed the x coordinate of that minimum, so I'm going to go and calculate the first minimum. And I'll go back and dig up that other place. It looks like it's at x equals 2, so I'm going to say I'm going to look between x equals 1 and x equals 3. I may have said that was 1 earlier, but that's definitely x equals 2. Yes, okay, and here's one where we can see, all right, some round off issue, some computation issue here. This means x equals 2 and y equals 0. All right, so it's going to be between x equals 2 and that maximum. So set up some. Have some of the work done. Here's the maximum happening. Now let's just look from there to 4. Okay, there we go. X equals 3.219. Then, after the x coordinate of the absolute minimum, I resume increasing and continue increasing forever. So that was 5.281. I just, looked up there, found the x coordinate at the absolute minimum. I knew I would be glad that I wrote that down. Okay, where are the rates of change of f negative? Okay, well, just like last time when we see something about the rate, we're going to want to translate that into something about the function. So rate of change is negative. That means that the function itself is decreasing. So where is f decreasing? Okay, which makes sense. They would ask us that right after they asked us when is f increasing. All right, so f is going to be decreasing before the relative minimum and between the relative maximum and this other relative minimum, which is also the absolute minimum. So we've got all the numbers we need already. We just need to use them. So that's going to be when x is less than 2. And also between x equals 3.219. Oh, whoops, did not realize that was not visible. Oh, and it's only getting worse. Hold on just a second. I know what's going on. I need to bring this back. Yeah, there we go. Okay, so x is less than 2, and also x is between that 3.219 and 5.281. All right, and how many points of inflection does f have? Right, well, let's just kind of look at the attitude of f. Okay, at first it's going down and then coming up, and that's smiling, right? So it's happy through here. But then, by the time it reaches this maximum, it's frowning. Okay, I'm seeing a frowning face. So there had to be a point of inflection somewhere in here, right? But then down here, I'm smiling again. Okay, and it looks like it just continues smiling forever. So I know that I've got a point of inflection around here, and somewhere in here. I don't know, it might be right here, but that sounds a little too good to be true. We weren't given any information about that in the statement of the question, which oftentimes we will, but I would say that I can tell you how many there are because I can say it goes concave up to concave down, back to concave up. That's 2 changes in attitude. I'm counting 2 points of inflection. Okay. And can I find the points of inflection using a calculator? I can, but because I know how to do calculus. It's kind of a trick question, and I didn't have time to get to this in class. But I think what I would say with this, not without calculus knowledge. We cannot find the actual points of inflection. They need to either be given to us, or we need to be given some sort of information about them. They happen in integers, so we could narrow it down that way. Something like that. Okay, but so the answer to this one, definitely not. And now, before I move on, I threw this fact in here because I saw it. It's an essential knowledge from AP Precalculus, and I'm not sure where else I'm going to hit it. I imagine we'll talk about this again when we talk about polynomials or even and odd functions, but polynomial functions with an even degree will have either a global maximum or global minimum. And by global, that's just a synonym for absolute maximum or absolute minimum. Okay, and that's just, think about y equals x squared, x to the fourth, that one we just looked at, and it has to do with the end behavior, which is something we will talk more about in the next unit. All right, so the last situation I've got for you is grass clippings are placed in a bin where they decompose. For t between 0 and 30, the amount of grass clippings remaining in the bin is modeled by a of t equals 0.9 to the t times the square root of 45t, where a of t is measured in pounds and t is measured in days. All right, so it asks for the average rate of decomposition of the grass clippings on the interval 20 to 30 days. Indicate units of measure and show the setup for your calculations. All right, I'll tell you what I'm doing, but I'm not sure I'm going to be, well, for this one, I'm definitely not going to be showing you the calculator. Right, what I'm going to do is I'm going to take a of 30 minus a of 0 divided by 30 minus 0 with a of t plugged into y1. I'm going to compute that with a calculator like I have many times before. Or probably should do a of 30 minus a of 20 divided by 30 minus 20 because we're looking at that time interval. Okay, but I go then and do that in the calculator, and I'm going to get negative 0.208 or negative 0.209. So negative 0.209. Okay, and indicate units of measure. Okay, well, A is measured in pounds, and T is measured in days. So pounds per day. And that's the average rate of decomposition of the grass clippings on the time interval 20 to 30 days. On the time interval 5 to 7 days is the amount of grass clippings decreasing at an increasing or decreasing rate. Right, well, they're just telling us that from 5 to 7, the amount is decreasing. So if they want to know if the rate is increasing or decreasing, that's going to be asking about the concavity of the graph of A of t on the interval 5 to 7. Okay. And I think that that's something we would be best off looking at a graph on the calculator to find out. All right, so I bring that back. I've got A of t typed into y1. I'm going to look on the time interval 5 to 7, so I'm not looking at anything I don't want to see. I can keep using that same y window because I don't think it'll actually be... Oh, no. Okay. Well, all right. You can't really see. So let's just say, all right, it looks like the number of grass clippings is in the range of 8 to 10 pounds. So I'm going to change the window again. Okay, so the y minimum, I'm going to make 8, and I'm going to keep the y maximum at 10. And then now we can see a little bit better that the graph is frowning. Okay, so it's concave down. Since the graph I can see is frowning a little bit. And as a result, I would say it's decreasing at a decreasing rate. If I want to see a more full picture of what's going on with this graph, I'm going to go to Zoom Standard and see that, okay, it goes up and then it starts to go down. And I think the shape at which it's decreasing does change somewhere in there, because we're only looking 0 or negative 10 to 10, but we were answering questions about 20 to 30 just before. So, all right, find the value of t at which get that in there. Find the value of t at which the amount of grass clippings in the bin went under 2 pounds. So really what I want to know is, when does a of t equal 2? And so I would go in here and, graph, actually go down, graph equals 2, and see, all right, well, I had that one where when they were dumping grass clippings in at the beginning, during the first day or the first few days, but I'm looking for this intersection that's happening much later, so I need to change the window. All right, so I'm going to let t run from 0 to, I feel like it said it stopped at 30 maybe, so I'm going to go 0 to 30. And then the y minimum is going to be 0 because we're not going to have any negative amounts of grass clippings in the bin, or we won't be interested in that. Okay, so it goes up and then down, and I think, yeah, we're going to see that. Okay, just barely. Okay, that was fortunate. So we're going to calculate that intersection like we already have a few times between blue and red. Give it a guess. Get t equals 27.154 days. And we can see that, after that time, the blue curve went under the red line. The amount of grass clippings was under 2. And so when was the amount of grass clippings in the bin above 5 pounds? So I'm just going to go in. I'm going to change it from 2 to 5. Look at the graph again. And find both of the intersections. And I think it'll be between those two times the amount, between these two times, the amount was above 5. All right, so calculating an intersection, blue, red, okay, that's going to give me the ending time value since I guessed over there. That's 15.925. And then the first intersection looks like it's happening closer to 0, so I'm going to calculate intersection between blue and red, give it a guess of t equals 1, and say, all right, that was 0.635. And that's when the amount of grass clippings in the bin was above 5 pounds. All right, and when did the amount of grass clippings in the bin begin to decrease? Well, the amount was increasing through here and decreasing there. Where we change from increasing to decreasing, that's the definition of a relative maximum. So I'm going to be computing a maximum here. That's to the left of it. I don't know, 15 will be to the right of it, because I can see that's the intersection, or at least around there. Give it a guess, let it think, and that's going to be when, that would be at t equals 4.746 days. And that's when the amount of grass clippings in the bin began to decrease. All right, now that's all the examples, all the calculator examples I've got for you for this lesson. There is a little bit more. There's a couple more pages of these notes about bottles, but I'm going to have that as a separate video. So if you're interested in that, you just keep on watching, and hopefully that'll play next. Otherwise, thanks for watching.